Okay, sorry for a few minutes. So it's my pleasure now to introduce session 11 plenary speaker, who is Steve Widdicombe, who is head of the Marine Ecology and Biodiversity Group at Plymouth Marine Lab in UK. So Steve is a marine ecologist with more than 25 years of experience in using field observation and large manipulative experiment to address issues relating to ecology, biodiversity, and ecosystem function. His work has focused on quantifying the effect of natural and anthropogenic disturbance, including climate change, on the structure, diversity, and function of marine benthic communities. And Steve will be presenting on how do we put all the pieces together to appreciate the bigger picture. The floor is yours.
Okay, thank you very much, Veronique. I have a bit of a confession to make this morning, feeling a little bit more nervous than usual, because what Veronique didn't tell you was that for many years she sat on the science assessment panel for our laboratory. So let's hope this goes well, because otherwise there's going to be a bad report going back. So lots of applause at the end would be very much appreciated. Okay, so I'm going to dive straight into this figure here, because I feel that it really nicely encapsulates sort of the work I have been doing and sort of the direction of travel in which I'd really like to be taking the science I do. As Veronique said, I'm an experimental ecologist, so my work very much focuses down in this bottom sort of left-hand corner, looking at the impacts of various climate change stressors on individual organisms in experiments that last maybe a few weeks, a few months. You know, some have gone out to a year or so. However, like many in this room, I'm probably not alone in ending a lot of my papers with some glib comment that, and as you can see from my results, you know, this will have implications for communities and ecosystem function, without actually taking that anywhere further. But it's difficult. It is really, as an experimental ecologist, it's really difficult to make that step up to making some meaningful comment about how what we see in our experiments, the data we produce, how that's going to affect populations, communities over scales. And there are two major challenges we face. The first one, time. You know, climate change is changing over years and decades that are so difficult to capture realistically in the kind of experiments we do. You know, these experiments, as I've said, are short-term duration, days, weeks, months. You know, and often what we look at is a shock response to a change in environmental conditions. Now, that's not to say that the data we get from those experiments is anyway not useful or can't be used, because those experiments are giving us an insight into the mechanisms by which organisms interact with these environmental conditions. But there's also complexity. The idea that we need to be moving into a world that we're conscious that there's multiple stresses acting simultaneously on marine organisms. They have a lot to deal with. They have a lot on their plate. And the interactions not only occur between species themselves, but also within species, that populations interact with each other and compete with each other, and actually individuals as well. And not just individuals, but within individuals, processes within individuals interact with each other. And one of the biggest elements of complexity comes when we start to consider, as we've seen in a number of talks this morning, the concept of climate versus weather. And many people have shown sort of graphs similar to this. These particular data come from a long-term observatory we run in Plymouth, the Western Channel Observatory, and these are carbonate chemistry values over the last 10 years. And I think they nicely demonstrate, you know, this concept of, you know, the variability within the year, this weather, this natural seasonal cycle with long-term trends, which is inherently the climate. But what we mustn't think of is these two things being decoupled from each other. They are intrinsically linked together. And often we think of the relationship between climate and weather akin to these two gentlemen down in the right-hand corner. If you're an organism or an ecosystem, you know, the thing that really hits you is the guy on the left. He's the one who's delivering the big knockout blows, these extreme events. And behind him all the time, the climate is making him bigger, is making him stronger, is making him faster, and making these events really hard to deal with. But there's something else going on as well, and we mustn't forget that not all the impacts of climate change are associated with these big events, these big mortalities or these big bleaching events. There's a chronic effect going on as well. And to sort of illustrate that a little bit further, I'm going to take you back to this study we did 10 years ago. And it was very much one of the first things we did when we started getting into this idea of understanding how high levels of CO2 could affect organisms. And we ran an experiment, a fairly short-term experiment with extreme pH values, but on a burrowing brittle star, a starfish that lives under the sediment. But the beauty about using this experimental model was that you can take the ends of the arms off this animal and it grows them back again. And you can then look at how the growth of this calcium carbonate structure looks under different CO2 conditions. And we obviously expected that the high CO2 would be a negative impact on the processes this organism had to do to regrow its arms. But what we found was the contrary. It was different. The animal actually grew its arms back more quickly with higher calcium carbonate content in the arms under high CO2 conditions. And of course, this perplexed us to start with, but the clue was in the last slide. These organisms have been dealing with the weather, the climate weather, for the whole of their lives and whole of their sort of evolutionary period. If they didn't have physiological mechanisms by which they were able to upregulate certain processes in response to environmental stress, then they wouldn't be lasting very long. I mean, we've all been dealing with this all week, where we come from the sunshine outside to the highly aggressive air conditioning that we have in here. So we've been adopting these physiological processes and this plasticity. Some of us physiologically, some of us more cleverly have gone to behavioral responses and brought a jumper with us. But in essence, this plasticity is all part of the response to high CO2, and we must consider that. But of course, it doesn't come free. It comes with a cost. What are the costs of this plasticity? So we went looking for what the payback might have been in this particular experiment. And when we looked at the musculature of the arm, the regrown arms, we found that under the very low pH systems, the muscles were reduced. So the organism was sacrificing the strength of these arms in terms of the muscles it put into them by being able to grow the actual structure itself. So this made me think about not considering organisms just as a series of, measuring response through a single physiological response or a suite of physiological responses, but trying to understand what the holistic response of an animal is going to be to an environmental stress. How is it going to deal with this? What choices is it going to make in order to compensate, one process over another process? What was really important? The idea being that you can increase your feeding to give yourself more energy to respond if your cost of living is going up. But that might mean the fact you've got less to invest in growth or reproduction. And rather nicely, there's a number of models that have been and are being developed that capture this kind of idea and start to give us an opportunity to bring the physiological data that we generate in our experiments into a context by which we can realistically find a gateway into scaling up to population models and community level models. So this happens to be a dynamic energy budget model, but there's a number of sort of model frameworks around that you can use. And by doing this, we can start to understand how, by the partitioning of energy within an organism, we can start to see how it's likely that these choices are going to impact upon those processes that have real resonance at a population and a community level. Feeding could change trophic interactions. If the organism is looking for more energy, it could change the way it reacts with its prey source or its as a secondary consumer of the way in which it interacts with primary producers, but also in terms of how much effort then goes into reproduction, how successful the organism is going to be. And this comes back to this idea of chronic change, the idea that you might not see in your experiment, large amounts of mortality, but if you're losing your ability to produce enough gametes for the next generation, eventually, some way down the line, your population is going to be unsustainable. And also growth as well. The organisms, are they going to start to become smaller? Are we going to get still as many of them, but actually we're focusing more on smaller organisms as they can't spare the energy to grow bigger? So what does it look like in practice? Well, this was an experiment we ran a few years ago as part of the UK ocean acidification program, and we ran, at the time, a very long-term experiment, 18 months exposure, where we exposed a series of intertidal animals to a range of high CO2 conditions and also an elevated temperature condition as well. And we collected a whole suite of physiological parameters as they responded to these environmental stresses. And then it's a very complex slide here, but in essence, what I'd like you to take from this, on the left-hand side was a suite of physiological measurements that we took from those experiments. But we blended those with observations from the field and from data we gathered from the literature, and also predictions from ecosystem sort of level environmental models to give us a context of how the future was going to look. And the structure that brought it all together was a bioclimatic envelope model, so that's similar to the work that William Chung's been developing with his group. And it gives us a way in which we can bring all this information together to try and understand how likely it is that organisms are going to be able to persist in different parts of the marine environment into the future. And what do the results look like? Well, we chose one particular organism from our experiments. This is a snail, an intertidal snail called Nucella lapillus. And what these data show you is if we look along the top line, we see if we go right to the far end, this is a combination of when we used the effects of warming and ocean acidification on those physiological processes. And we looked at how different those populations are likely to be from the normal conditions if none of this stress was occurring. And I think the take-home message from here is that the combination of those two stressors had the biggest effect, and also none of the impacts were not the same in the different parts of the distribution of this organism. And a lot of that had to do with the provision of food, the primary production that was changing in different parts of this area, so that they didn't have enough of the food to cope with the stresses they were having to face in some of these areas. There we go. And models like this about how you scale up these physiological responses can actually have a management application as well. This is some work that's recently been done by a colleague of mine at PML with her colleagues in CFAS. And it works around the concept of this large fish index is indices used by fisheries management to give an indication of how healthy the fish stocks are. And it's basically a simple equation of the idea being that it's the proportion of the large-bodied fish in your whole community. So the idea being that a healthy community has lots of large-bodied fish, and therefore as you impact on that community, either through fishing or through other kinds of stressors, you remove the large-bodied organisms, and then you get an increase in much more smaller-bodied animals. So it's a simple metric to try and appreciate the overall health of the fish stocks. And what we've noticed what has been noticed in the North Sea is that prior to an intense period of fishing, on the bottom left in the high LPI, there was in essence the populations were large, dominated by large fish. There was an intense period of fishing activity in the North Sea, obviously. In the late 1990s or through the 1990s, which seriously impacted this index and reduced the LFI down, particularly across the eastern coast of the UK. But fishing effort has been reduced and fishing management practice has been put into place, and hopefully the hope was that this index would increase. But it hasn't been increasing as much as we would have expected to have increased by the reduction of the fishing pressure. And what this paper by Anna and her colleagues have shown is that by looking at different areas of the North Sea and actually employing one of these size spectrum dynamic bioclimatic envelope models to try and recreate in model form what those communities are likely to look like, and therefore use models to calculate an expected large fish index for those areas. What she's actually found is that in areas that are quite strongly controlled by environmental conditions, such as the northwest North Sea and the southwest North Sea, this model is predicting that actually the recovery of the LFI is unrealistic. We shouldn't expect it to be able to recover just because we've removed fishing, because the environmental stressors are now playing a role to reduce the size spectra of these communities. And actually our management targets that we've put in place are unachievable, despite the fact that we've removed fishing. So this is an illustration that understanding the physiology helps us start to ground truth whether the sort of the management processes we put in place are realistic. But to make things even more complicated, populations are not all the same. This was a study by Pierre Colosi and colleagues who looked at a range of different, took populations from different parts of their biogeographic range. In this case, again, it was another snail species, and looked at a suite of environmental responses to an experiment whereby they elevated CO2 and warming. And what they found was that the response of these populations was very much driven by where they were collected from. So the local populations had very different responses to ocean acidification and to warming. And particularly those species at the range edges showed much more compromised by the environmental stress than those in the middle. Okay, so we've seen a lot about species range shifts, and the idea being that organisms are likely to be shifting north or south. But we also need to be mindful that even though temperature may be driving them one way, other stressors such as ocean acidification could be cutting off that escape route and actually crushing these distributions down to a much smaller level. Okay. And that shouldn't come as a surprise to us. I mean, we know that there's huge amounts of variability in environmental conditions, and this work by Christian Vargas and his team on what is in essence an amazing sort of experimental system along the coast of Chile shows just how variable the environmental conditions can be from place to place. And when they looked at the experiments on organisms that have been taken from these different places and using the same ocean acidification parameters to test them, they saw that there was enormous differences in response between the same species but from different populations, all based on what they'd experienced in the past and what they've become used to. So this shows us that to consider a species just a broad, this is what species X does, it's a little bit too simplistic still, and we need to be mindful of the population it comes from and what it's experienced in the past. And to add yet more complexity as well, we fail to consider organisms as individuals. You know, none of us respond to the same stresses in the same way, yet we expect the animals we bring into our experiments and put into our containers to all be the same and all respond in the same way. And I bet we've all looked at graphs like this with these big error bars and gone, oh no, I'm going to have to do something with transformations now. What we should be doing is looking at these data and saying this variability is actually perhaps the key message I'm seeing from the data that I've generated. What is it that's underpinning this variability? You know, there's winners and losers in that population. And that is what is underpinning as well this idea of localized adaptation and acclimation to these stresses. So don't despair when you see graphs with massive great variation around your mean. Rejoice and look into what it is that it's actually telling you. And something we very rarely consider as experimentalists is the importance of gender. For the gender of the organism that you're looking at actually can have an effect on the response you see. This was work done by Rob Ellis, looking at the mussel Mytilus edulis, and again, using high CO2 as a challenge. He looked at the metabolic products produced by these organisms and saw a large difference between the response of the males in his experiment and the females. Now, that's maybe not surprising, given that the physiological priorities and responses of the different sexes may be very different, particularly at different times of the year. And this made him think about just how prevalent this idea of ignoring these gender responses was in the literature. And he did a meta-analysis whereby he looked and he found that only in less than 4% of the studies he could find, they actually considered whether they were males and females that they were experimenting on. But in the experiments that he did find that they reported on whether the balance of males and females and the difference between the responses of the different sexes, he found that there were significant differences in the way in which these organisms responded based on their gender. But interestingly, it wasn't always the way you would expect. The idea being that perhaps, when the female organisms are producing eggs, they're putting a much greater energetic investment into these structures. Therefore, they're likely to be more susceptible to additional stresses that increase the cost of body maintenance. But it wasn't always that way. So it's mindful that we try and understand what it is that's driving the differences between them. And there could be, and these sort of non-sex discriminated experiments could well be masking some of the effects. For example, if you get a mortality of 25%, you might think, well, that's okay, my population can handle a 25% mortality. But if they're all males or they're all females, that has very different interpretations in terms of the long-term success or the viability of the population. So in summary, no experiments or studies are a perfect mimic for climate change, except perhaps one, and that's the one we're doing on a global scale, but it's probably not wise to wait until the results are in for that one before we make management decisions. So we need to find ways in which we can take the increased understanding of biological processes and make them far more relevant to estimates and predictions at ecosystem and community levels. Complexity and variability is all around us and increases as we move across these spatial, temporal, and organizational scales. And we need to accept this and work with it, but not just accept it, but also be mindful that some of the answers we're looking for is hidden in this variability. And we should look to this variability to give us the clues and the answers that we're looking for. Also appreciate where the system has been, because when we go to the field and we take animals out of the sea, we often ignore what they've been exposed to, what they've learned to tolerate, how they've evolved over the period of being there. We're all a product of where we've come from, and it's true for the organisms on which we experiment. But equally, we need to find ways to pull our sort of greater understanding of physiological and biological processes and impacts together in order to be able to really understand how the whole thing works together. And what's really pleased me this week is there's been a real shift from previous meetings I've gone to, that there's a lot more evidence of people thinking across disciplines and thinking how they bring their understanding together to make bigger statements and more useful and applied statements as well. But to echo a message that I've seen a lot as well this week is that we need to evolve. We need to co-evolve this. It's not a case of running an experiment and saying, right, now I need to find a modeler to tell me what this all means. Or modelers saying, right, I've built this model now, I've got some data missing, I need to find myself an experimentalist. We're only really going to address this if we sit down together at the beginning and actually co-evolve these processes together so that the models are there to represent what it is we're doing, but the experiments are also there to actually support and develop these models together. And it's an iterative process as well. The models aren't the end point. They're the point at which they challenge us and identify the problems that we've now got with our understanding, and we come back again, and we start again, and we come through this period again, the whole system again. And eventually we will start to move up that line will get up into that top right-hand corner. Thank you. I'll leave it there.
Thanks, Steve. We've seen that for SDG 14, SDG 5 matters too, so that's good. We have time for a couple of questions before the coffee break. Well, I have a quick one. I'm sure you've been showing experiment with OA and warming. Are you, and I'm sure you're looking at that at PML, I'm going back to the nanoplastic stuff because it's another stressor, which is really now part of our world. So are you doing any kind of experiment looking at, these, the way they impact reproduction, growth, and stuff like that? Can you say a few words about that? Does it matter? Are they going to adapt?
Again, it's a question of trying to understand what is it that actually the nanoplastics are doing. And if you look at the framework of the organism itself, and the first obvious thing is toxicity, but actually I think the key thing that I'd like to understand is how it affects part of that whole dynamic energy budget in terms of the food supply. Is it making food more difficult to come? Are organisms becoming satisfied and full up based on eating sort of organic products or particles? So it could affect it there. We've seen how plastic affects ballasting as well. So I'm conscious, and yeah, plastics is a big thing at the moment, but it is, again, it's only one of the multiple stressors. So I think what I would like people to do is try and find frameworks whereby we don't get obsessed by a particular stressor, be that pollution or even light, noise, climate change, but we find model structures whereby we can encapsulate the understanding we have to see how these stresses affect the function of those organisms. And if we build them right, we should be able to put in the multiple stresses whenever we find them.
Thank you.
Time for coffee. Oh.
Yeah, just...
Go on, just shout.
Shout.
Yeah, thanks very much. Right on, brother. It's great talk. I guess we've done some gap analyses and see all these meta-analyses, very small numbers in terms of interacting factors used in experiments. I guess I like your impression of how we're doing. You're talking about what we should do, but where are we right now? I mean, if you had to give us a report card as experimentalists in terms of studying the kinds of things we're supposed to study, like, for example, using low feeding in some of these treatments, how are we doing right now, if you gave us a report card?
Okay. I think we're doing great. And I'll tell you why. Okay. We've done a huge amount of work, and I look back at it and I hear some people say, oh yeah, but you've used the wrong pH, or you've used the wrong this, or you haven't learned anything, you've done. But actually, there is no, for the most part, there is no bad experiment. It may not have been targeting the thing you wanted to look at, but there's always information to be gleaned from those. And I think the thing that we've moved on considerably from is providing, as I said, providing those tools that enable us to take the knowledge that we do have and start to actually interpret it in a way that makes much more sense and is much more applicable. I don't think we're anywhere near fully understanding the system. And I think what we have now moved away from, actually, is a thought that we did understand the system. I think OA was a perfect example where a few years into the research, we thought we had it cracked. This is what happens. Calcification changes and this and that. And actually, we're much better now in accepting the things we don't know.
I guess as a quick follow-up, I'm surprised you didn't mention the need to standardize protocols in these experiments, because one thing we see a lot when we see summaries of OA research, et cetera, is need to use common protocols to be able to make comparisons more easily.
Don't do it.
Okay.
No. The problem with standardizing, it forces everyone to look at the same thing and forces uniformity. The beauty, I mean, I've presented a number of ways in which we can move from one place to another, but don't everyone do this. Find other ways as well. The variety of different ways tells us different things. And I think the pressure to say, oh, we all have to do the experiments in the same way, it completely limits the amount of information we can glean, because some of the experiments on the really high CO2 treatment levels have given us an insight into physiological mechanisms that we maybe wouldn't have seen had we all been doing 1,000 ppm as our stressor. So I'm afraid I'd like people to go and find things out.
That's a good point. Thanks.
Can you pass on the microphone? Thank you, Myron.
Thank you, Steve. Great talk. Yeah, I'm with you. Please do not standardize, because the beauty of understanding some of these changes is actually to document and understand fully the environmental variability. We know from the stuff we've done in Chile, we know from the stuff we've done in UK, stuff done in Germany. Every organism have different tolerances to these changes, responses to these changes, so do not standardize. I have a question as well. The majority of the experiments done before, of course, have been a very good lesson learned for some of our work. But also one of the things I think we've been missing, and missing a trick here, is try to understand what are the kind of things that will help the organisms to counter-effect some of these challenges. And I wonder whether you have an opinion about that. Because this is something that, as well as stressing organisms, what's going to be the comeback to overcome all the trade-offs? And I think that's quite important as well. What's your opinion?
Not a sort of an earth-shattering vision on how we're going to go there, but I do agree with you that by understanding these trade-offs, it certainly gives us an insight into how we might help support those organisms, implement that physiological plasticity. So make sure that we're not doing things to the system that actually hampers their ability to do that. So I suppose a simple example would be if you're aware that a particular stock requires more energy to be able to deal with this, you don't go and harvest the hell out of its primary food source. You put the buffer in there, you help the organism to display those plastic responses to the best of its ability. And then the classic example is the idea of building resilience into areas through supporting biodiversity on the understanding that there are some things you can't stop. You're going to get species lost. So don't be taking species out before nature then comes along and takes its subset out as well.
Thank you.
Okay, we'll applaud for Steve again.